Ever really stop and think about that cold drink you're holding, or the food in the fridge, or
Yeah.
just how nice the AC feels?
Yeah, it's easy to forget what's going on behind the
We
scenes.
just take it for granted, you know?
Yeah.
But it all comes down to some really fascinating thermodynamics, a kind of hidden world making things work.
Absolutely. It's fundamentally about moving heat, specifically moving it from a cold place to a warmer place, which doesn't just happen on its own. Nature wants to go the other way.
Exactly. And that's what we're diving deep into today, the world of refrigeration cycles. You've sent over a great set of materials, textbook stuff, new innovations, even some surprising history.
It's a rich topic.
So our mission is to pull out the key ideas, give you those aha moments, and really show how clever and, frankly, vital these systems are.
Okay, let's unpack it. We're drawing from all these sources you sent.
Sounds good.
So let's start right there. Moving heat. Heat naturally flows downhill, right? Hot coffee cools down. Easy.
Right. Hot to cold.
Yeah.
Spontaneous.
But refrigeration is forcing it uphill. Is that a fair way to put it? That's a great analogy, yeah. It's compelling heat to move from a low temperature area to a higher temperature one. That needs a special device.
Yeah.
An energy input.
Okay, and this is where refrigerators and heat pumps come in. You said they're basically the same. That kind of blew my mind a little.
Fundamentally, yes.
Yeah.
Mechanically, they're often almost identical. The difference is the goal.
Okay.
With a refrigerator, your objective is simple. Keep the inside space cold. You achieve that by removing heat from it.
And dumping that heat outside is just what happens.
It's a necessary byproduct.
Mm-hmm.
You have to put that heat somewhere warmer, like your kitchen. The goal is the cold space.
Makes sense. So the heat pump flips that.
Exactly. The objective is to keep a space warm. It achieves this by absorbing heat from a cold source. Think cold outdoor air, maybe well water,
Okay.
and then delivering that heat into the warmer space, like your house. Same process, just focusing on the heat delivered instead of the heat removed.
Wow. Okay, that clicks now. Two sides of the same coin. So how do we measure how well they do this? I hear COP, coefficient of performance, thrown around.
COP is the key metric. It's simply the desired output divided by the required input. What you want divided by what you pay for in energy.
So for a fridge, the COPR, that's the cooling.
Right. COPR is the cooling effect, the heat removed. Call it QL divided by the work input, rent it in.
And for the heat pump, COPHP.
That's the heating effect, the heat delivered, QH divided by the same work input, wet it in.
Okay, simple ratio.
And here's the really neat part. Both COPR and COPHP can be, and often are, greater than 1.
Wait, greater than 1, so you get more heating or cooling out than the electricity you put in. How does that work?
Because you're not creating heat from electricity, like a resistance heater does. You're moving existing heat using electricity.
Yeah.
So for every unit of electrical work you put in, you might move, say, 3 units of heat.
Ah, okay. It's a heat mover, not a heat creator.
Precisely. And there's a direct relationship. COPHP always equals COPR plus 1 for the same conditions.
So a heat pump is always delivering at least as much energy as it consumes, just by definition.
At the very least, yes. Which makes it inherently more efficient for heating than just turning electricity directly into heat, like in an old-style electric radiator.
That's a game changer for thinking about heating efficiency. That's
Yeah.
huge. Okay, and sticking with units for a second, what's this ton of refrigeration? It sounds so old-fashioned.
It is. It's a historical unit, but you still hear it. It comes from the ice-making industry. It's the rate of heat removal needed to freeze 1 ton, that's 2,000 pounds of liquid water at 0 Celsius, into ice at 0 Celsius over a 24-hour period.
Okay, that's quite specific. What is that in modern units?
It works out to about 211 kilojoules per minute, or 200 B2 per minute.
So, like, how big is that in real terms? My home AC, for example.
Well, a typical house, maybe around 200 square meters, might need something like a 3-ton air conditioner. That's roughly 10 kilowatts of cooling capacity. It gives you a sense of scale.
Got it. Okay, so we've got the core idea, moving heat uphill. Now, the cycles themselves, let's start with the theoretical ideal, the reversed Carnot cycle. It's the benchmark, but why don't our fridges actually use it?
You're right. It represents the absolute maximum possible efficiency between 2 temperatures.
Wow.
It uses 4 completely reversible processes, 2 isothermal, meaning constant temperature heat transfer, and 2 isentropic, meaning constant entropy during compression and expansion. Purely theoretical perfection.
Perfect on paper, but
But it's just not practical to build. There are a couple of major sticking points.
like what? What's the big problem?
Well, first, compressing a wet mixture, part liquid, part vapor, is really hard on compressors and very inefficient in practice. Standard compressors hate liquid.
Okay, bad for the hardware. What else?
And second, expanding a high-moisture refrigerant efficiently through a turbine is also very difficult to engineer reliably and affordably at this scale. Plus, maintaining perfectly constant temperature during heat exchange in the real world. That's another hurdle.
So it's a beautiful theory, but doesn't translate well to engineering reality.
Exactly. Its value is as a standard of comparison. It tells us the absolute best we could do, so we can judge how well our actual cycles perform against that limit. It's a yardstick, not a blueprint.
Right. Which leads us to the cycle that is the blueprint, the workhorse, the ideal vapor compression refrigeration cycle. This is in pretty much everything, right? Fridges, AC, heat pumps.
This is the dominant cycle, yes. It cleverly sidesteps the Carnot problems.
How does it do that?
Two main ways. First, it ensures the refrigerant is completely vaporized before it hits the compressor. No wet compression.
Oh, okay, solves that problem.
Second, it replaces the complex, expensive, and tricky turbine expander with a simple, cheap throttling device, usually an expansion valve or just a long, thin capillary tube.
Ah, so simplify the expansion part. Does that cost efficiency?
It does introduce an irreversibility, so yes, it's inherently less efficient than a perfect reversible expansion. But the massive gain in simplicity, cost, and reliability makes it the winning choice for most applications.
Makes sense. So walk me through the 4 steps in this cycle. How does it work?
Okay, imagine the loop. Start at the evaporator. This is inside the cold space, like the coils in your freezer. Here, the cold, low-pressure liquid refrigerant boils, absorbing heat from the space around it. It turns into a low-pressure vapor. It's like it's soaking up the heat.
Got it. Soaks up heat, becomes a gas.
Then that low-pressure vapor goes to the compressor. This is the energy input part. The compressor squeezes the vapor, increasing its pressure and its temperature significantly. Think of a bike bump getting hot.
Okay, hot, high-pressure gas. Where next?
To the condenser. These are the coils usually on the back of the fridge or in the outdoor AC unit. Here, the hot vapor releases its heat to the warmer surroundings, your kitchen air, or the outside air. As it cools, it condenses back into a high-pressure liquid.
So that's where the heat gets dumped.
Exactly. And now you have a high-pressure, warmish liquid. The final step is the throttling device, the expansion valve or capillary tube.
The replacement for the turbine.
Right. This device causes a sudden large pressure drop. As the pressure drops, the temperature plummets. So you end up with a very cold, low-pressure mixture of liquid and vapor, ready to go back into the evaporator and absorb more heat.
And the cycle repeats.
And the cycle repeats, continuously moving heat from the cold side to the hot side.
That's brilliant. I can picture it now. The freezer coils or the evaporator, the warm coils on the back or the condenser actually makes visual sense. And you mentioned temperature changes have a big impact.
They do. A useful rule of thumb. The COP generally improves by about 2 to 4%. For every degree Celsius, you can raise the evaporating temperature or lower the condensing temperature. Minimizing that temperature lift the cycle has to work against is key.
Okay, but that's the ideal cycle. Reality isn't ideal. What happens in the actual vapor compression cycle?
Right. The real world introduces irreversibilities. Things like friction in the pipes, heat leaking in or out where you don't want it. These all degrade performance compared to the ideal model.
So what are the main differences we see in practice?
Well, for one, designers often ensure the refrigerant is slightly superheated when it enters the compressor.
Superheated. Warmer than boiling.
Yeah, just a few degrees above its saturation temperature. It's a safety measure to guarantee no liquid droplets get into the compressor, which could damage it. It costs a tiny bit in extra work, but protects the equipment.
Okay, a practical precaution. What else?
You also get pressure drops. As the refrigerant flows through the evaporator, condenser, and all the connecting pipes, friction causes the pressure to decrease slightly. That's an energy loss.
Makes sense. Friction always takes a toll. Anything else?
Yes. On the other side, after the condenser, the liquid refrigerant is often deliberately subcooled.
Subcooled. Colder than condensing.
Exactly. Chilling it a bit below its saturation temperature before it hits the expansion valve means it enters the evaporator colder. This increases its capacity to absorb heat. You get more cooling effect for the same amount of refrigerant circulating.
Ah, so that actually helps capacity. Interesting.
It does. And finally, the compression process itself isn't perfectly isentropic in reality. There's friction inside the compressor and some heat transfer occurs. All these factors mean the actual COP is always lower than the ideal COP.
Like in that example I saw, where these real-world things chipped away, maybe dropping a COP from, say, 3.97 down to 3.93. Small changes, but they add up.
Precisely. Every little bit of friction, unwanted heat transfer, or deviation from ideal conditions impacts the final efficiency. It highlights why good engineering design is so important.
Okay, so understanding these deviations brings us to second law analysis. Why go beyond just COP? What does this extra layer tell us?
COP tells you the overall efficiency, how much cooling you got for your energy buck. Second law analysis, using the concept of Exergy, is like an energy audit. It pinpoints where in the cycle the biggest losses or Exergy destruction are occurring.
Exergy destruction, that's lost potential.
Exactly. It's the destruction of the potential to do useful work, caused by irreversibilities like friction or heat transfer across a finite temperature difference. It's always calculated relative to the surroundings at dead state temperature, usually TNO.
So it helps target improvements, find the weak links.
Precisely. And often, the results are quite revealing. For instance, second law analysis frequently shows that the simple, inexpensive throttling valve,
The replacement for the turbine.
yeah, that little valve is often the single largest source of Exergy destruction in the entire cycle. It can account for, say, 30–40% or even more of the total lost work potential in some cases.
Wow. That tiny, simple part causes the biggest irreversible loss. That's kind of counterintuitive.
It is. Because it's a highly irreversible throttling process, pressure drops dramatically with no work being recovered. This analysis really highlights why replacing it with an efficient expander turbine would significantly boost efficiency, even if it's often not practical from a cost or complexity standpoint.
So this analysis gives you a roadmap for where the biggest gains can be made, and there's a specific efficiency measure for this.
Yes, the second law of efficiency, often written as YLE, edit 2. It's the ratio of the actual COP to the COP of a completely reversible cycle, operating between the same temperature limits essentially, the reverse Carnot COP. It tells you how close your real cycle is getting to theoretical perfection.
Okay, very useful for engineers. Now let's shift gears to the refrigerants themselves. This has quite a history, doesn't it? Early ones were pretty nasty.
Definitely. Back in the mid-1800s, you had things like ethyl ether. Later came ammonia, carbon dioxide, but also things like sulfur dioxide, methyl chloride. Highly toxic stuff. There were accidents, leaks from early home refrigerators in the 1920s that caused fatalities. Big public concern.
Yeah, I can imagine. That must have driven the search for something safer.
It absolutely did.
Yeah.
Which led to the development of CFCs, chlorofluorocarbons, in the late 20s, early 30s. Think R11, R12, often known by the trade name Freon.
The miracle refrigerants.
They seemed like it at the time. Non-toxic, non-flammable, stable, efficient, cheap. They took over the market for decades. Refrigerators, AC, aerosols, solvents, everything.
Until the ozone layer problem surfaced.
Exactly. In the mid-1970s, scientists realized these incredibly stable CFC molecules were drifting up to the stratosphere and catalytically destroying the ozone layer that protects us from harmful UV radiation. A massive environmental crisis.
Triggering international action, like the Montreal Protocol.
Right. Leading to a phase out of the worst offenders, the fully halogenated CFCs like R12. The industry then shifted towards HCFCs like R22, which had chlorine but also hydrogen, making them break down faster and have much lower ozone depletion potential, ODP.
But still some ODP, so the next step was HFCs.
Correct. Hydrofluorocarbons like R134A, which replaced R12 in cars, or R410A, which replaced R22 in many AC units. These have zero ozone depletion potential because they contain no chlorine.
Problem solved.
Well, zero ODP, yes. But HFCs turned out to be potent greenhouse gases contributing to global warming. So now the focus is shifting again towards refrigerants with low global warming potential, or GWP.
Like R32, I hear that mentioned now.
R32 is a good example. It's an HFC, so zero ODP, but its GWP is only about 1/3 that of R410A. So it's a step in the right direction. There's also renewed interest in natural refrigerants like ammonia, hydrocarbons like propane, isobutane, and CO2, despite their own challenges like toxicity or flammability.
So what makes a good refrigerant today, besides the environmental factors? What are engineers looking for?
Thermodynamically, you need suitable pressures and temperatures. The evaporating pressure should ideally be above atmospheric pressure to prevent air leaking in if there's a small leak.
Okay, keep air out.
And the condensing pressure needs to be manageable well below the critical pressure of the fluid. You also need a decent temperature difference, maybe 5 or 10 degrees C, between the refrigerant and the air or water it's exchanging heat with for heat transfer to happen efficiently without needing huge coils.
And other properties.
Ideally, you want something non-toxic, non-flammable, non-corrosive, chemically stable, cheap, and with a high latent heat of vaporization.
High latent heat means?
It means it absorbs a lot of heat when it evaporates. So you can circulate less refrigerant to get the same amount of cooling, which can mean smaller pipes, smaller compressor, potentially higher efficiency, It's a complex balancing act. Ammonia, for instance, is great thermodynamically, cheap, zero ODP GWP, but toxic, which limits its use mainly to industrial settings.
Right. So many trade-offs. Okay, we've covered the main cycle in refrigerants. Let's explore some more advanced or alternative systems. Heat pumps seem to be getting more attention.
They definitely are. The higher initial cost is often offset by lower running costs, especially compared to electric resistance heating. We talked about air-to-air systems being common.
But they can struggle when it gets really cold, right? Frosting.
Exactly. Below about 2 to 5 degrees C, frost builds up on the outdoor coil, blocking airflow and heat transfer. The system then has to periodically run a defrost cycle, which uses energy and temporarily stops heating.
Are there alternatives that avoid that?
Yes. Water source heat pumps, using well water or lake water, have higher COPs because the water temperature is more stable than air and they don't have the frosting problem. But you need access to that water source, and the installation is more complex.
And ground source, geothermal.
Ground source or geothermal heat pumps are very efficient because the Earth's temperature several feet down is remarkably constant year-round. No frosting, stable performance. But the installation involves burying extensive loops of piping, which is expensive up front.
So different options depending on location and budget. What about those units that do both heating and cooling?
Ah, the dual-purpose units. Very clever. Since an air conditioner and an air source heat pump use mostly the same parts, compressor, coils, fan adding and reversing valve lets you switch the flow direction of the refrigerant.
So the indoor coil becomes the condenser in winter.
Exactly. And the outdoor coil becomes the evaporator. It allows one system to provide heating in winter and cooling in summer. Very cost-effective in climates that need both, like motels or homes in many parts of the U.S.
Neat. Okay, what about really big temperature differences? You mentioned Cascade systems.
Right. If you need to cool something to a very low temperature, or the difference between the cold space and the ambient temperature is just too large for one cycle to handle efficiently, you use Cascade refrigeration.
How does that work? Stacking cycles?
Pretty much. You have 2 or more separate refrigeration cycles operating in series. The condenser of the lower temperature cycle rejects its heat, not to the ambient air, but to the evaporator of the higher temperature cycle. They're linked by a heat exchanger.
And the benefit?
It allows each cycle to operate over a smaller, more manageable temperature range, which significantly boosts the overall COP compared to trying to achieve that huge temperature lift with a single cycle. It reduces the total work needed. You might even see 3 or 4 stages for ultra-low temperatures, like in industrial applications.
Okay. Then there's multi-stage compression. Similar goal, but different approach.
Similar goal, improving efficiency over large temperature lifts, but usually uses the same refrigerant throughout. Instead of separate cycles, you might have 2 compressors in series with some form of cooling in between, or often a device called a flash chamber.
A flash chamber, what does that do?
It's basically a tank where some of the liquid refrigerant coming from the condenser is allowed to flash evaporate at an intermediate pressure. This cools down the remaining liquid refrigerant before it goes to the main evaporator. The flash vapor is often rerouted to the inlet of the second stage compressor.
And that helps. How?
It reduces the total work the compressors have to do. It's a form of intercooling and regeneration within the cycle itself. It can give a really nice bump in COP compared to single-stage compression for the same conditions. Maybe boost a COP from, say, 4 to almost 4.5 in some cases.
Interesting. What if you need cooling at different temperatures? Like my fridge freezer.
Multi-purpose refrigeration, a common challenge. Instead of 2 separate systems, you could use one compressor but throttle the refrigerant differently for each section. You might throttle the refrigerant partially to reach the fridge temperature, say 4 degrees C, then take the remaining liquid and throttle it further down to a much lower pressure to get the freezer temperature, maybe negative 18 degrees C or lower. Both streams eventually combine and go back to the single compressor. It's a clever way to serve multiple cooling loads with shared components.
Very practical. No, for something really specialized, liquefying gases, getting things down to cryogenic temperatures below -100°C?
Exactly. Essential for things like separating air into oxygen and nitrogen, producing rocket fuels like liquid hydrogen and oxygen, storing natural gas as LNG, and for lots of scientific research like superconductivity.
What's the big challenge there? Just getting that cold.
The main hurdle is cooling the gas below its critical temperature. Above that temperature, no amount of pressure will turn it into a liquid. And for gases like nitrogen, oxygen, hydrogen, helium, those critical temperatures are extremely low, way below what a standard refrigeration cycle can reach.
So how do they do it? You mentioned the Linde cycle.
That's one classic method. It uses a combination of techniques. First, High-pressure compression, often in multiple stages with cooling in between to make it more efficient. Then, crucially, a regenerative heat exchanger.
Regenerative.
Yeah, the high-pressure gas coming from the compressor is cooled down by the cold gas that didn't liquefy in the previous pass through the cycle. So you're using the cold product stream to pre-cool the incoming stream.
Ah, recycling the coldness.
Exactly. After this regenerative cooling, the high-pressure pre-cooled gas is expanded through a throttling valve. That sudden pressure drop causes a further significant temperature drop due to the Joule-Thomson effect, hopefully getting it cold enough to partially liquefy. The liquid is drawn off, and the cold vapor goes back to cool the incoming gas. It's a bootstrapping process.
Ingenious. Okay, let's switch tracks again. Gas refrigeration cycles. Using gas instead of a phase-changing refrigerant, like running a jet engine cycle backwards.
That's a good analogy for the reverse Brayton cycle, yes. Instead of condensing and evaporating, the working fluid remains a gas throughout the entire cycle, usually air.
Why use that? You said phase change helps efficiency.
It does. Gas cycles generally have lower COPs than vapor compression cycles operating between the same temperatures, mainly because the heat transfer isn't isothermal. The gas temperature changes as it absorbs or rejects heat.
So what's the advantage then?
Simpler, lighter components. No need for bulky evaporators and condensers in the same way. This makes them very suitable for applications where weight and size are critical, like cooling electronics on aircraft.
Ah, niche applications. Can they get super cold?
They can, especially if you add regeneration. Similar to the liquefaction cycle, you can use a heat exchanger, so the cold gas leaving the turbine pre-cools the warmer gas going into the turbine. This lets you achieve much lower temperatures than a simple gas cycle, making them useful for some cryogenic applications too.
Okay, now for a really different approach. Absorption refrigeration. You said these are heat-driven, no compressor.
That's the defining feature. They're attractive when you have cheap heat available, maybe waste heat from a factory, geothermal steam, or solar thermal energy. They replace the energy-intensive mechanical compressor with a thermochemical process.
How does that work, in principle?
In a common system, like ammonia water, the low-pressure ammonia vapor coming from the evaporator isn't compressed directly. Instead, it's absorbed into water. This liquid solution can then be pumped to high pressure using a simple liquid pump, which takes very little energy compared to compressing a gas.
Okay, so you pump the liquid mixture, then what?
Then you add heat and a component called the generator. This heat boils the ammonia out of the water solution. Now you have high-pressure ammonia vapor, just like you'd get after a compressor in a standard cycle. This vapor goes to the condenser, throttles, evaporates, and absorbs heat, then returns to the absorber to repeat the cycle.
Wow, that's complex. Using heat to drive the separation, what are the downsides?
They are definitely more complex, bulkier, and more expensive up front than vapor compression systems. Their COPs are also generally lower, often less than 1. And they need larger cooling towers because they have to reject not only the heat absorbed in the evaporator, but also the heat added in the generator.
But the input energy is heat, which could be cheap or free.
That's the economic driver. If waste heat is available, the low electricity cost can make them viable despite the lower COP. But their performance is quite sensitive to the temperature of the heat source.
And there was that quirky camper version, propane-fired, using hydrogen.
Right. Some smaller absorption units, often used in RVs and for camping, use a clever trick. They add an inert third fluid, usually hydrogen. The presence of hydrogen modifies the partial pressures, allowing the ammonia to evaporate at low temperatures without needing a pump or any moving parts at all. They run silently on propane heat. Quite ingenious for off-grid use.
Amazing. Okay, last category. Solid-state systems. Thermoelectric refrigeration. No moving parts, no fluids. Sounds like magic.
It's based on some fascinating physics discovered back in the 19th century. First, the Seebeck effect. If you join two different conductive materials in a loop and heat one junction while cooling the other, an electric current flows. That's how thermocouples work for measuring temperature.
Okay, heat difference creates electricity.
Right. And you can actually use this for power generation, though usually at low efficiency. Think of the radioisotope thermoelectric generators, RTGs, used on spacecraft like Voyager heat from radioactive decay makes electricity. Very reliable, no moving parts.
And the cooling part.
That's the Peltier effect, basically the reverse. If you pass an electric current through a junction of two dissimilar semiconductor materials, one side of the junction gets cold and the other side gets hot. Heat is literally pumped from one side to the other by the flow of electrons.
So you just apply voltage and one side cools down.
Essentially, yes. You build modules with many of these junctions in series thermally, but parallel electrically. Apply DC voltage, And one faceplate gets cold, the other gets hot. You need to dissipate the heat from the hot side, of course.
What are they good for? The efficiency isn't great, right?
No, the COPs are much lower than vapor compression. But their advantages are huge in certain niches. They're incredibly small, simple, silent, very reliable, no moving parts, no fluids to leak, and offer precise temperature control. Perfect for small coolers, cooling laser diodes, medical sample storage, things like that.
Fascinating field. Okay, well, we've covered a lot of ground. From the basic idea of pushing heat uphill through the workhorse vapor compression cycle, the complexities of real-world losses and refrigerant choices.
Cascade systems for ultra-low temps, clever multi-purpose designs, gas cycles, heat-driven absorption, and even solid-state thermoelectric cooling.
It really is an ingenious area of engineering. We hope this deep dive has given you a solid understanding, maybe demystified your fridge or AC a bit, and highlighted some of the clever thinking involved. Lots of memorable details in those sources you said.
Definitely. It's a field that's constantly evolving, driven by needs for efficiency and sustainability.
So that leads to our final thought for you, the listener. Considering all these different approaches, vapor compression, absorption, the thermoelectric, different refrigerants, using waste heat, what do you think comes next? Where are the biggest challenges and the most exciting potential breakthroughs in the coming years for refrigeration and heating? Especially with the push for sustainability, what stands out to you as the next big frontier in managing temperature efficiently? Something to ponder.